Hello everyone, this is Professor Nelson from Electronics. On this occasion, we are going to make a very useful and practical tool to check the status of our electronic components. For this we will need some LED bulbs that are damaged like these ones here. Here we have several types of LED bulbs. In these LED bulbs, what usually breaks down most frequently are the LED diodes. Meanwhile, the electronic board usually remains intact, so we can use it to make our tool. Now, as you can see, we have two types of LED bulbs. One has the electronic components next to the LEDs, and this other has the LEDs separated from the electronic board. However, that's not a problem since both work the same way. So, any type of LED bulb will work for this project. So, without further ado, let's continue with the video. For this example, we're going to use this LED bulb, which has its electronic board separated from the LEDs. All the LEDs are damaged, making it useless. So, the first thing we're going to do is disassemble the bulb and remove the electronic board. Okay, this would be the electronic board. Now, let's test it to make sure it's working properly. Before testing the electronic board, we're going to make some changes so it can work in our project. As you can see here, this would be the electronic circuit of our electronic board, in which you can see that it has several components, the most important of which would be the two cables that we have here. The red one, which is positive, would be connected to the anode of the LED diodes, or the LED strip, and the negative would be connected to the cathode of the LED strip. Additionally, it has other components, but the one that interests us most on this occasion would be the resistor on pin 4 or CS. The resistance it has there right now. This one here would be a 1.5 ohm resistor. That resistor controls the current. The current that goes to the LEDs to this point. That current will be determined by the value of that resistor. And with the help of this formula, we can determine the current flowing, in this case through the LEDs. And if we use the formula, the peak current will be equal to 0.373 divided by 1.5 ohms. This will give us a current of 248 milliamps as peak current. However, the current to the LEDs will be half the peak current. Therefore, we will have a current of 124 milliamps that will circulate towards the LEDs. We don't need that amount of current for our instrument. So, we must first reduce that current to a fairly small value. How small? Well, up to about 50 milliamps. It could be 20, or it could be 30, or even 40. The lower the current, the better for us, since we don't need an excess of current. Therefore, we will modify this to reduce the current going to the LEDs. The next modification would be as follows. Right on the positive side, on the positive wire, we're going to connect an additional protection resistor. This resistor can have values from 10 to 20 ohms. It can be a quarter of a watt or a half watt. Either power will do. After that, we're going to connect what would be a voltmeter like this one here. Preferably a 3-wire one, with red for positive and black for negative. The positive wire can't be greater than 30 volts. And the signal or test wire. After the resistor, we're going to connect some Zener diodes. In this case, we're going to connect 2 Zener diodes, each 1 watt. And we're going to connect them directly like this, where the cathode of the Zener diode is connected to the resistor, and the anode of the Zener diode is connected directly to the cathode of the LED, or to the negative terminal of the electronic board. This one will be 10 volts, and this one will be 15 volts. Both are 1 watt. After that, we'll connect the voltmeter. The positive lead directly to the voltmeter or red wire of our voltmeter, and the black lead directly to the anode of the Zener diode. This would be our voltmeter. And this would be the signal or test lead. Now, why do I use 2 1-watt Zener diodes? That's to be able to dissipate the power in 2 components. And so that the voltage in this case is only 25 volts. Because as I mentioned, the voltmeter can't have a voltage greater than 30 volts. Therefore, 25 volts is perfect for powering our voltmeter. Then we will connect a 4.7 kilo ohm resistor from here. A 1/4 of a watt, which would be more than enough. We're going to connect it to the output wire or green wire of our voltmeter. And here we're going to connect the components we want to measure. It could be a microwave diode, it could be a common LED, or it could be a Zener diode, or any other component that has a working range of 25 volts. That is, here we put our components to measure. In this case, this would be positive, so I can connect a Zener diode here. And I can measure it with respect to negative. Or I can place a normal LED. And I could also measure it this way. So that would be the circuit we need to build. We're going to test the circuit first, and then we'll assemble it. But first, we're going to modify the resistor that controls the current, so that we have a much lower current than the 120 milliamps, which could burn out our Zener diodes. That's why we're going to reduce the current, because if you multiply the 120 milliamps passing through here, and multiply that by the 15 volts of this Zener diode, it gives us almost 2 watts. And that's practically going to burn out the Zener diode. But if we modify the resistance and reduce the current, our diode won't burn out. So those are the modifications we're going to make. The first thing we're going to do is change the resistance of pin 4 or CS, which controls the current. So let's do that. Okay, let's change the resistance. The resistor we're going to use is going to be a 10 ohm resistor. It can be in this format. Or in SMD format like this one here, 10 ohms. So let's solder this resistor. With the modification done, let's test it. Now let's build this circuit. But before finishing assembling the entire circuit and connecting our voltmeter, let's test the circuit we just built to confirm that we have approximately 25 volts across the two Zener diodes, and that the current has decreased from 120 milliamps to less than 30 milliamps, which would be the result of having inserted 10 ohms of resistance. Well, for that we are going to use our multimeter and set it to direct current voltage. Turn it on and measure the voltage across the Zener diodes. And there we have 25.7 volts. Now we're going to measure the current. We put our multimeter in direct current. Open the circuit and, with the help of the multimeter, close the loop, negative to negative, and positive to the anode of the Zener diode. Turn it on and pay attention to the multimeter. There we have 24 milliamps, which is less than 30 milliamps, and it's much less than 120 milliamps. With that, we would confirm that the circuit is working up to this point. Very good. So now we proceed to install our voltmeter. Very good. The circuit is finished. Now let's test it. We're going to install a Zener diode and an LED to confirm that our circuit is working correctly. To do this, we turn on the electronic board, and we have almost 24 volts. We install an LED, and we have 1.9 volts, which is very good. Now we install a Zener diode. And we have 14.6 volts. It's very good since it's a 15-volt Zener diode. Now we invert it. And we have 0.7 volts, which is good, since that's the value of a forward bias diode. Now what happens if I short-circuit the output? Well, it shows us 0 volts, which means our circuit is working perfectly. So, with the tests over, we move on to mounting the circuit in a box so we can use it more comfortably. So let's move on to that. Okay, most of it's done. Now let's place it in the box and make the rest of the connections. Okay, now for the rest of the materials to assemble our tool. First we need a box, and in this case, we'll make a custom-made box to hold all the components we've seen. Additionally, we need a switch, 2 tips of a multimeter to be able to make the measurements, and their respective connectors, which we'll place in our box. So, without further ado, let's move on to the assembly on the box. The first thing we'll do is glue our electronic board in that position. We glue it with a little hot silicone. We also apply a little to the resistors so they don't move. We wait for it to dry and then make the rest of the connections. Okay, now we place our voltmeter and glue it. Now we place the switch. But first, we're going to solder a wire to one end. This would be the negative, and this would be the positive terminal of the multimeter leads, or the one that would be connected to the green wire. We connect the voltmeter first, negative to negative, same as this other one to negative. That is, both negative terminals would have to be connected. The negative terminals are now connected. Now the positive terminal. The positive terminal would have to be connected just after the resistor. As the circuit indicates, after the resistor, we would have positive. The negative terminal has already been connected to the negative terminal. The green wire would be connected right to the end of the 4.7 kilo resistor. The positive wire we have here should also be connected to the end of the 4.7 kilo resistor. Okay, almost everything would be connected now. We just need the power cable. Let's connect it. First, we'll connect one directly. We'll connect this other wire to the switch. Okay, everything would be connected now. Now we secure the power cable, apply a little glue, and then cover it. Okay guys, we've finished assembling our measuring instrument. As you can see, all the connections are there. And it turned out pretty good. The connections are the same ones we just described in the circuit. So if you make the same connections, you'll have the same result. Here we have the 4.7 kilo resistor, which is this same resistance. And this is where we'll place the components. And we're going to measure them using the tips of a multimeter we're not using. There you go. See how it turned out? It looks pretty nice. We can turn it on. And we have almost 24 volts. And I repeat, it turned out great. So now we're going to test it. Let's measure some components. Here we have several components to measure. We have an LED diode, we'll connect positive to positive and negative to negative. And we have 1.92 volts. A microwave diode. We connect it to direct current. In this case, cathode to negative and anode to positive. And there we have 7.5 volts. Remember that this can't be measured with a regular multimeter. Therefore, this tool is very useful for measuring this type of microwave diode. Now, a Zener diode. Here we have a diode. And we have to connect the positive to the cathode and the negative to the anode. And it is a 15-volt Zener diode. We invert it and measure it, and it should give us 0.7 volts. There we have 0.7 volts, which means this Zener diode is in good condition. We can also check what the LEDs in the LED bulbs would be. Let's measure. And it tells us it's giving us 5 volts. That way you can check. This one doesn't work. This one's fine. This one's bad. So, that's how you can use this tool. Now if they short circuit, we see 0 volts. Nothing happens. If we touch the tips, nothing happens either. It won't hurt you. So this tool is excellent for our job, which I advise you to do. Okay, so that concludes the video. So guys, don't forget that if you like the video, a like helps the channel a lot. See you in the next video. Bye-bye.